Good morning, everybody. Thank you very much, Linda, for that kind introduction. And thank you, everybody, for being here. It is really a great pleasure to be able to touch base again. And I would be very happy to talk about the cutting edge and upcoming PAT technologies regarding DO. And I'll open up, as Linda mentioned, a little bit towards dissolved CO2 as the byproduct of oxygen in aerobic fermentation and cell culture upstream operations as well. So a little bit of introduction about why dissolved oxygen in aerobic fermentation is a CCP, a critical process parameter, and then we'll jump in with how we characterize DO in our process. I apologize also for my rough voice, as in the great continent of Asia, it's warm and my allergies are feeling refreshed. So apologies in advance. Always begin by reminding everybody just how reactive oxygen as a species, chemical species, is. Remember, oxygen is what puts our rockets in space. And it does that by reacting so fast to the oxidized species like hydrogen in this case, and creating such an exothermic reaction. So when oxygen is dissolved in aqueous solution, that is in water, it doesn't slow down. It is still just as reactive. The reason why we do not see the flame when oxidation is happening in aqueous solution is that the heat that is exerted from the oxidation reaction is absorbed by the water, high capacity of water quickly. And in aqueous solutions, it's really not as difficult to find oxygen, because yes, oxygen in the air is much more abundant, around 21% in the atmosphere. And it's a low solubility gas in water, but water itself has around 86% by weight oxygen. So when we do not want oxidation happen in aqueous solutions, this reactivity is bad, and it creates rust and corrosion on our, let's say, stainless steel platforms, right? But life has learned, that is, living cells that are depending on aerobic fermentation have learned how to harness such reactivity and put it to good use. The fish in the ocean, us breathing the air and grabbing onto the oxygen for our catabolism in the cells, we know exactly how to put that reactivity into good use. And also for, as I said, the solubility of oxygen, for the providing the oxygen in the soluble form, oxygen follows the exact same principles as any other gas solubilizing in aqueous solution. That is, as Dalton tells us, when gases are mixed in the gaseous form, the partial pressure of each gas species determines how much it has presence in the interface of the gas with the other phases, solid or liquid, right? And then Henry's law tells us that the solubility of the gas inside the liquid form, inside the aqueous form in this case, is determined by that partial pressure of that gas species in the gas. So in simple words, the more abundant the gas is inside our bubbles, inside the liquid or at the interface, then the more solubility of that gas species, in this case oxygen, we have in the liquid form. So the solubility of oxygen essentially then depends on a few more parameters as well. Salinity or chlorinity of the aqueous solution is one parameter. More salts you have in the solution, less solubility of oxygen you have at hand. And so then it becomes the matter of measuring solubility of oxygen, or let's say the presence of solubilized dissolved oxygen, or DO, in the aqueous form. So we have two strategies here at hand. On one strategy, we can go ahead and estimate the precise or absolute, let's say, concentration of oxygen dissolved in the aqueous form. And for that, we need to bring all the parameters that affect solubility: partial pressure of oxygen in the gas form, and essentially relative humidity, barometric pressure, gauge pressure, uh, salinity, chlorinity, and therefore through empirical equation, come up with the milligram per liter, ppm or ppp, depending on the range of solubilized oxygen in the air, in the water. We can calculate and report that concentration. However, our measurement technique, our DO probe, let's say, that is measuring the dissolved oxygen in the aqueous form, is only still measuring the partial pressure, essentially. And the presence of oxygen there is depending on how much transfer there is from the gas bubble into the liquid phase. So the easier way to go about, and a little bit less precise way to go about, let's say, is to compare the dissolved oxygen presence to whatever we have at saturation and the 0 point when there is no oxygen present. So if without the presence of dissolved oxygen, we calibrate the DO probe, and then we, with the presence of saturated under the conditions that we have, temperature, salinity, so far and so forth, then upon that calibration is now relevant to those conditions, we can measure anything between and report it as percent saturation. And because such small presence of dissolved oxygen is not critical in biomanufacturing, let's say upstream biomanufacturing, then usually we follow such a relative measurement principle. It's rare to be measuring all the way down to ppb, for example, in breweries or in finished product in breweries, when we do not want even a few ppbs present in, for example, power plants in the water that is the coolant then essentially in the cycle. We do not want even presence of 1 or 2 ppbs of dissolved oxygen. Then we are, of course, able to have the precision and precisely report that. But remember, 1 ppb is parts per billion. It's like I take a small jewel, put it somewhere on planet Earth, and ask you to go find it, right? It's that challenging for the probe to report ppb levels of oxygen. But we have the probes that have such precision. It's just that in biomanufacturing, it's not often that we need such precision, so we can easily go with relative measurements. So touching base a little bit back on what really determines the solubility of oxygen, you can see here, for instance, in pure water and under ideal conditions, we have about 9.2 milligram per liter solubility of oxygen. But salinity and chlorinity, once they increase, look at how it's decreased in 4 molar KCl solution, almost less than 25%, right? And it can be the other way around as well. But with temperature, it's the other way around, right? So the higher the temperature, the lower the solubility of oxygen. So at 37 degrees Celsius, where most fermentation and all cell culture is taking place, then you have such lower concentration of oxygen soluble. Around perfectly, I can say 3 or 4 ppm in the media, in the broth of our fermentation broth or cell culture broth, right? So as a result, we are really limited by the low solubility of oxygen in our fermentation. And that really opens up the next topic in our discussion, how dissolved oxygen stands in fermentation. So any aerobic fermentation, namely burning glucose as the most readily oxidized and available carbon source for the fermentation, needs quite a bit of dissolved oxygen to complete that oxidation process, or let's say total aerobic respiration, and burn that carbon source all the way to CO2 and water. So each molecule of glucose needs 6 molecules of dissolved oxygen to burn it all the way to 6 CO2. And that CO2 that's produced and breathed out then comes out that dissolved CO2 coming into the cytoplasm, then coming into the broth, right? So combined with such low solubility of oxygen, as I mentioned, then the oxygen immediately becomes the limiting nutrient when we are dealing with aerobic fermentation. This is why in aerobic fermentation and cell culture, we are depending heavily on homogeneous mixture and a good mixing strategy in the stirred tank bioreactors, and also good aeration techniques, and make sure that we have a very robust CFD. Inside the stirred tank bioreactor, the bubble residence time is maximized. The bubble size is minimized so that we have maximum specific surface area and we do not have heterogeneity because we're such limited in providing the oxygen at such low solubilities for our fermentation. So when you look at the catabolic pathway for energy production in the steam room, in the mitochondria of the cells, right? If glucose goes without oxygen all the way through glycolysis, it ends up as pyruvate, and then the loop is complete, coming out as lactate, right? In anaerobic respiration. But by doing that, the cell only gains 2 ATPs for energy. If oxygen comes in and that pyruvate can now enter the TCA cycle, and it can only do that with abundant oxygen present, then the oxidation process is complete. Pyruvates go through to CO2, and then each glucose can give up to an extra 36 ATPs. So at the end of the day, without oxygen, you can get 2 ATPs. With oxygen, you can get up to 38 ATPs. The energy economy is no brainer. It's day and night. So without oxygen, it's energy bankruptcy. This is why in biomanufacturing, we now rarely see anaerobic fermentation. Cell culture, no way, because the cells are always oxygen dependent. And in fermentation, it's only when we have anoxic, let's say, or let's say a strict anaerobe species at hand, then we do not need the presence of oxygen, and we have anaerobic respiration at hand. And you can imagine how slow, how inefficient those fermentation runs be. So in my classes, I always give the analogy that carbon source, the glucose, is like the money you have in the bank account, and the oxygen is like the pin you have on that account. It doesn't matter how much money you have in the bank, unless you have the pin, you cannot spend any of it. So oxygen then is ruling the entire economy of the cell growth and metabolism, essentially. So how is then agitation and aeration helping us in keeping the KLA, let's say, the oxygen transfer rates inside the stirred tank bioreactor? So 3 terms that you need to keep in mind. First one is gas holdup. That is how much of the gas through that robust agitation from the sparger on the bottom all the way up where the gas is coming out of the liquid form into the headspace, you can keep, you can maintain and give time for the transfer to happen. In this case, turbulency helps, and also turbulency helps in the mass transfer rate. And most importantly, tiny bubbles, the smaller the bubbles you can create by creating good agitation, the more specific surface area, volumetric surface area you can provide, and therefore you can have more robust transfer rates, right? So in that fashion, the impellers inside the stirred tank bioreactors act in two forms of homogeneity. First is axial movement, which is essentially keeping the bubbles down, and then the mixture also going in a spiral vertically for homogeneity, and then radial dispersion when you sure that you have the liquid dispersed equally and homogeneously throughout the diameter of the stirred tank bioreactor. So when the legendary Danny Wong and Art Humphrey, the pillars of biomanufacturing, right, back in the 70s and the 80s, were selecting the right candidate design of the bioreactor for these biomanufacturing industries that were coming into the picture, right? They had many different designs available to them. Bubble columns, or let's say fluidized bed bioreactors, were big at the time, but they were smart. They knew that once you start scaling up the bioreactor to humongous scales that we have today, 30,000 liters, 40,000 liters, very common in fermentation and cell culture. And in fermentation, we can go all the way to 150, 200,000 liters. Those humongous stirred tank reactors, they knew that the real challenge will become heterogeneity, and keeping it homogeneous essentially would be the real challenge. So, and they were right. These days, our scale-up engineers do not hate anything more than heterogeneity inside the stirred tank bioreactor, those large stirred tank bioreactor. And the heterogeneity is really bad when it becomes the situation in aerobic fermentation as well. So because of that, and because of the inherent, let's say, good mixing with the active vegetation, right? In the stirred tank bioreactor, those legends gave us the design, and you can see today, 99% of the times we are dealing with a stirred tank bioreactor for our aerobic fermentation and cell culture. And so in the stirred tank bioreactor, then how much oxygen you can actually put into the liquid depends on very numerous, let's say, empirical conditions. Namely, the partial pressure of oxygen in the gas bubble is the major driver, but also there are a few other parameters at hand. The fermenter pressure, that is the gauge pressure on top, is a factor, comes into play as a positive factor. The more pressure you have in that space, the more solubility of oxygen you have at the bottom in the liquid. The vapor pressure is competing essentially with the oxygen, so it has a negative impact for us. And also the hydrostatic pressure, of course, of the liquid column inside the tank also plays a factor. So the hydrostatic pressure, as you can see here, is helping with the solubility in the bottom, but it's a double-edged sword, because if you have a very tall liquid column, you have good solubility and a lot of oxygen dissolving in the bottom, but very little in the top, and essentially you will have a very strong gradient along the height of that hydrostatic column. So that is essentially creating heterogeneity by itself, mass transfer throughout the vertical axis, right? And you do not want that. So this is why we don't deal with a lot of height, and we want to keep the height to diameter ratios below 3 when we are dealing with such large fermenters, right? But this is what you need. All this empirical calculation is what you need in order to calculate precisely how much milligram per liter, ppm or ppb, solubility of oxygen you have, dissolved soluble oxygen you have at hand. But for relative, remember, with present saturation, you do not need to use such empirical approach. You can essentially compare everything at all times with the 100% saturation. So you have all these empirical parameters essentially embedded in the 100% saturation conditions. That is why it's much easier to go with percent saturation in aerobic fermentation. So how is DO then maintained inside the tank? Well, inside the tank, we have two sides now. The demand side, which is coming from the gas bubbles, air or oxygen, or a mixture of air and oxygen. And then, the supply side. And the demand side are essentially the cells that are growing in the tank and picking up oxygen from the liquid bulk as dissolved oxygen and putting it into good use. So on the supply side, we have the oxygen transfer rate, OTR, which is like any other transfer rate from a phase to phase in mass transfer, is determined by a driving force. That is how far away we are from saturation. CL star, remember, is the saturation concentration. Again, here around 3-4 ppm. And CL is the concentration that we have at hand at any time. When we are away from saturation, you have a better driving force, you are transferring more. When you approach saturation, then the driving force dies and you can transfer anymore, of course. And then a constant. And that constant is what we call the KLA. Because we don't have much to say about the driving force, the saturation is predetermined. The temperature, the salinity, it's pretty much given to us by the recipe that we have at hand. So we can't do much about the driving force. All our efforts go above to make sure that our KLA, the constant, then is maximized. And so maximize KLA means maximize oxygen transfer rate for us. And KLA essentially is built of two forms. One is the KL, which is the constant, essentially the coefficient for oxygen transfer coefficient. And A is that gas-liquid interface specifics area. Tiny bubbles have a large A, specific volumetric surface area. And large bubbles are bad because they have such low A in this regard. So KLA together then determine the whole equilibrium. On the demand side, then we have modeled in such way that we can characterize different species based on their different level of demand for oxygen, right? So we characterize them as a specific essentially consumption rate times how many cells we have present. What's the concentration of the cells present at each time? And so once we're on our way into the aerobic fermentation, like I said, oxygen becomes the limiting nutrient right away. In those situations, then whatever oxygen you are providing for your cells gets picked up and put to good use right away. So the oxygen as a limiting nutrient means that the demand side is equal the supply side. So in that case, the OTR is equal the OUR, oxygen uptake rate, right? So looking at the demand side a little bit more closely, you can see with our aerobic fermentation, namely E. coli, it's very oxygen hungry, 10 to 12 for the QO2. That is millimole oxygen per gram dry weight of the bacteria present in the liquid. So E. coli under aerobic fermentation becomes the champion for expression of all those recombinant proteins and essentially products, right? Value-added products. And look at yeast, Saccharomyces cerevisiae. It's still aerobic, like Pichia, but the QO2 is smaller than E. coli. The reason is that the yeast is a little bit slower in growth than the bacteria. So it is just as oxygen hungry, but because it takes its time a little bit for the growth phase, then we have lesser demand at hand. So E. coli can have a doubling time of as low as 20 minutes, even 15 minutes, right? But for the yeast, it's a couple of hours down to 1 hour. So that more essentially timed growth means that we have time to provide the oxygen for it itself. And mold is even slower than yeast, so you can see the numbers come down when we are dealing with mold. And when we're dealing with cell culture, animal cells, look, the numbers are not even comparable to mold. Why? Not because, again, cell culture doesn't need oxygen as much. It's just as oxygen hungry, but now it's so slow that we really have time to provide it with the oxygen, right? So for CHO, for example, which is the E. coli counterpart in cell culture technologies, the doubling time is at best 22 hours. So every day they're doubling, not every 20 minutes or 15 minutes. So their slow metabolism then gives us the chance to provide the oxygen. And so the challenge becomes the transfer part again, the supply part, because on the demand part, we pretty much map it out and we always know that we have such high demand. On the supply side, then we need to come up with a rough, or let's say fairly accurate situation when we need to know what the KLA is we're dealing with, right? So because then again, the driving force is pretty much set for us. And this is where the KLA for each fermenter that we are using becomes a thumbprint for that fermenter. Small or large, doesn't matter. We need to know before we put it into use what KLA capacity it has. And for that, we have essentially two approaches. The steady-state approaches into calculating what the KLA is, and the unsteady state approach. Unfortunately, KL and A, the coefficient, and the volumetric specific surface area cannot be calculated mathematically. And they cannot even be measured standing alone by themselves. So we cannot calculate them, therefore we cannot calculate KLA. So when I say calculate, I really mean measure. However, fortunately for us, we can measure KLA empirically inside every tank that we manufacture, so we can have that fairly accurate KLA assumption at hand. So in the steady state approach, we have the sulfide method, and we have, of course, the fermentation growth also. In the sulfide method, which is not as common anymore, we have the whole tank filled up with a sulfite solution. And sulfite is oxygen hungry, like our cells, right? When we start aerating it with the oxygen at the constant rate with the constant agitation, every molecule of oxygen that comes in from the spargate gets picked up by the sulfide right away, turning it into, oxidizing it into sulfate. So from time zero up to where we have all the sulfide consumed, we have the sulfide concentration at any time of measurement, and we have a sulfate concentration. And then the rate at which the sulfide is consumed and the sulfate is produced, take sample, go to the spectrophotometer and characterize the sulfate, right? Sample after sample, every minute, every 30 seconds, you can then come up with a table and say, this is the rate at which I was providing the oxygen, and that rate essentially will determine how much KLA I had at hand with the equation down here, right? And so why is it not as common anymore? Because of the fact that you need to come up with the sulfite solution, and then the samples you need to take is a little bit elaborate to take to the lab and measure the concentration. Of course, when you expose your samples to the air, the oxidation keeps going. There's a little bit of inaccuracy inherent in there. The unsteady state approach, however, is where more conveniently we can come up with a accurate or fairly accurate KLA. Then you only need to fill up the tank with just water, and we need to sparge all the oxygen out with nitrogen, ample nitrogen. Then at time zero, we start with the air, switch to air from the nitrogen. and keep a constant aeration agitation rate, then at any time, every minute, we take a measurement, not by taking an offline sample. The beauty is that we have now an inline, accurate, fast action DO sensor. And that will give us an inline measurement at all times. So if we plot then the DO saturation that we had at hand, of course, it needs to be calibrated, then we can build that graph. And from that graph, for example, if you plot the natural log of C star minus CL versus time, then the slope of that, because of the equation we have at hand, right? That is the rate of the change in the concentration of oxygen is that driving force times the KLA. And with a little bit of math, if you assume that the KLA does not change with time, which is a good assumption, if you have a constant agitation aeration, and integrate upon that differential equation, then you come up with the equation that the natural log of that driving force at all times is equal to the minus KLA times the timestamp that you had at each sample point, right? So then that plot becomes a line, and that slope then can give us the KLA. Simple as that. And you don't need any chemical reaction for it. And this is why the unsteady state approach is most commonly used, especially in the large tanks. And of course, when it comes to the DO maintained inside the fermentation, because the steady state with the fermentation inside is closest to the conditions that we have at hand. For one, we're not dealing with water, so we're dealing with the real-time salinity and chlorinity. Of course, the steady state method with fermentation is the most accurate. But in this case, based on the thin liquid layer theory, the two-film theory, you need to fill up your fermenter with media, sterilize, bring the seed into it, start the fermentation as if you are running a everyday fermentation run, and then somewhere in the exponential phase, somewhere where cells are growing exponentially at a constant rate, then you have your window or going in there, everything is constant. Growth is constant, consumption is constant, agitation and aeration are kept constant. So if you start taking measurements again with that calibrated inline DO probe, then you can build that graph and essentially come up with the KLA, because the OTR is constant, the KLA is constant, and you can figure out by connecting it to the OUR, the QO2 times X. So because it's still limiting and you have all the parameters in between the equation, right? Except for the KLA, you can figure out what the KLA is. But you can imagine just how elaborate that is. You have to have a fermentation in a large fermenter for that. So this is not as common for that reason as well. All right, now we know how the DO is essentially maintained and figured out in our fermenter. Then the challenge at hand is why is DO still such a CPP, such a critical factor? Well, this is because when we have the dissolved oxygen coming from the gas bubble to our cells, every molecule of oxygen needs to go through a laminar layer of liquid around the gas bubble into the liquid bulk, then travel through that liquid bulk, get through the laminar layer around each cell, get inside and get consumed for the metabolism. So we have 1, 2, 3, 4 gateways for the oxygen to go through before it's picked up and consumed. So here, we know empirically that when we insert our inline DO sensor, if in the liquid bulk we have 30%, 40%, let's say, saturation at hand, then empirically, again, we know that it means happy cells. It means that our cells are picking up enough oxygen. So this is good because the point of measurement is virtually right in between the supply and the demand. The challenge is when you have a solid state, let's say anchorage dependent or biofilm at hand, when you have the solid state present as well. So it's not two phases only, gas and liquid. Now we have gas, liquid, and solid. Examples are biofilm reactors in fermentation, when you have mold, for example, creating mycelium inside the fermenter, or in cell culture when you are dealing with, for example, anchorage dependent cells. HEK cells on microbead carriers, they've been the backbone of vaccine manufacturing for decades for us. In those cases, the cells are not every man for itself in suspension. The cells are attaching to a surface, creating a film on the solid surface. So in that case, every molecule of oxygen needs to still go through the gas bubble into the liquid, travel through the liquid bulk, get to the surface of that solid state. There's a laminar layer, get through it, get through the solid state, essentially to get to the cell, get through the cell membrane, get to the mitochondria surface, and then consumed for the oxidation. And now one, still two, three stages on this side, but then 4, 5, 6, 7. So 3 extra stages essentially for the oxygen to go through, 2 stages extra on this side, right? And that means now what can we do? We can only still put an inline DO sensor into the liquid bulk. That's what the technology is still at hand. And because now it's so far away from the point of consumption, remember, that's where it really matters, how much oxygen we have here. So you might, in many cases, still reach 30%, 40% saturation here, but your cells deep into the solid phase are suffocating. They're not getting enough oxygen. So here is where the technology needs to make a breakthrough, because we need to be able to characterize the dissolved oxygen presence here, where it matters, and we're not there yet. So another challenge at hand that makes DO such a critical parameter is where you have, you're hitting the ceiling. You cannot reach the DO that you need to have with just air supplied into the tank. So in cell culture, we are really limited because too much aeration, too much agitation is shear rate. Cell cultures do not, the mammalian cells do not have cell wall, do not have that tank armor that the bacteria and mold and yeast have on, right? So they really care about shear rate. You can shear them with too much stress. And so over there, we are very conscious with agitation and aeration rates. So in high cell CHO, for instance, for monoclonal antibody or other protein production, we often choose to go up on concentration of oxygen instead of going up on aeration rates, right? Or agitation in that matter. And in fermentation, of course, in high cell E. coli or yeast, then the consumption is so much that air is not enough to provide the oxygen. What happens when we pack more and more of molecules of oxygen inside the bubble? The concentration of oxygen goes so high that we start oxidizing the nutrients, the complex nutrients in the media, complex sugars, vitamins, and lipids. And not only once they're oxidized, they fall out of the equation, they become what we call readily oxidizing substances, ROSs, free radicals. And those free radicals are really bad because they rush into the cell, and they, at high levels, they can kill the cells. So you start losing the VCD inside the bioreactor, right? Even on the smaller levels, they can still bad because they interfere with the expression system, and they can really radicalize the GAG pathways, for example, for methylation. And you can have over-methylated proteins, which really takes away from the potency and the identity of the product that you will end up with. So we need to keep an eye on these ROSs. And our suggestion for those high cell density equations is keep an eye on the ORP. So when you are installing the pH probe from us, you are also installing an inline ORP with that platinum grounding of the reference solution on our, for example, 3253i pH sensor, right? So when you have free ORP, essentially, when you are using our probes inside the bioreactor, why not use the data? And by keeping the ORP levels under a good threshold, that is namely around plus 150, 175 millivolts, then you can make sure you're not creating too much ROSes, right? So your metabolism is intact. And then by adding a little bit of more air, not too much, because then again, air at top, air bubbles burst and create cavitation and kill the cells. We can build a trade-off. We can build a balance. Keep ROSes down and keep aeration up by essentially marrying the DO, the ORP sensor, and the DO sensor together and maximizing our yield. Okay, how is the DO measured in line then? In AQS form, you have really two methods or technologies at hand. The amperometric measurement, which has been established for decades and has served us very well for the past 3-4 decades. And now, recently, it's been really challenged by the optochemical method, right? In gas phases, of course, we have the laser, which is really solid, but unfortunately, in liquid, we cannot use such sophisticated technology yet. So when you compare the new cutting edge optochemical measurement versus the amperometric one, the optochemical has some advantages and intrinsically it can be more precise. How so? The optochemical sensor works based on fluorescence quenching principle. So you have a chromophore at the tip of the optochemical sensor, where excited with a beam coming from the light source at the top gives off the fluorescence. And with presence of oxygen, that fluorescence is quenched, is picked up by the molecules of oxygen in there. That's simple. So essentially, what you have at hand in this cutting edge measurement technique is a excitation still happening at the tip, and then the emission wave coming back up tells us how much DO we have present at the tip. So when we don't have any oxygen, we have maximum emission. When we have saturation oxygen, we have minimum emission. So the phase shift is considered, and then calibrated sensor can tell us what's in between, right? But the challenges that the optochemical sensor faces, namely the tiny bubbles sticking to the surface here, and also the sedimentation, the biofouling, and also hydrophobic proteins making a layer, leaving a layer here, are the two challenges that the amperometric sensors face as well. But we might have actually a solution for both. Besides, with the amperometric sensors, whenever you change the membrane, you change the electrolyte, remember, you have to give it a minimum 6 hours of polarization with the new electrolyte and the fresh membrane in there. That is a lot of downtime for the maintenance of the amperometric sensor. With the optochemical sensor, the downtime can be 30 seconds because that optocap with the chromophore in it, once you take the old one out and you put a new one in, there is no liquid, so there is no polarization. You can put it to use right away. So that's a huge technical underground advantage. But also for those two big challenges that the DO measurement faces, and in this case, CO2 also faces those challenges as well to some extent, is the bubble sticking to the surface, to the tip of the sensor. And those bubbles you can see create a noisy signal. However, we have a special finish, extra finish on that tip now. We call it the anti-bubble optocap. And that noisy signal that you saw when the bubbles are sticking, you can see how noisy it can be, really now is enhanced greatly with the anti-bubble optocap. So the signal to noise ratio without those tiny bubbles, some of them you can't even see, right? the signal to noise ratio, look at the red here, is enhanced significantly. And I know you say this is nice, but what does it mean in the process? That noise, is it really a big deal? Yes. When we're dealing with essentially high cell density with fed batch strategies, we usually want to loop our fed batch with DO. And look at the yellow. The yellow is exact same sensor, OptoCap, without the finish, without the anti-bubble technology. See how noisy it was when our partners in Brazil, Amaris, came back and said, the signal is so noisy, we cannot loop the addition of glucose for our yeast. And we offered the anti-bubble OptoCap. So with the orange, look at the anti-bubble. When the glucose is present, the DO is down. As soon as the glucose is exhaust, it's gone, then we see a spike in DO. And then you know the PID controller knows it's time to add a little bit of more glucose. Then glucose comes in, the DO goes back down, it's being consumed again. Then is exhaust again, add a little more exhaust, add a little more exhaust, add a little more. So the fed batch strategy can be mapped precisely based on those sharp peaks coming from the DO probe. And without the anti-bubble, the customer was not really able to have that precision in addition of the glucose. It's the same deal with when we are dealing with CHO, with the high cell density CHO with fed batch, it's still glucose. Or with the methanotrophic yeast when we are adding methanol into our mix. And look at the purple. Remember the ORP measurement from the pH sensor? ORP doesn't care about its platinum patch. It doesn't care about bubbles. However, there is a lag. It's skewed to the right. Why? Because when oxygen goes out, it takes a few good seconds before the ORP starts declining. So at first, we suggested looping with the ORP, and they were still not happy with it. So we had to bring the ACE out and give them the anti-bubble OptoCap. So it's really a differentiator, great differentiator, and it can be a powerful PAT tool in your arsenal. And there is really no more justification as not to have that anti-bubble finish on our sensors. Here you can see zoomed down just how much signal to noise ratio is enhanced, right? And another breaking through technology is our ISM sensors. This really requires a second session, but our digital sensors, intelligent sensors, have a chip in the head that holds on to your calibration. Your calibration is not in the transmitter or in the biocontroller anymore. In this case, what we gain is that we can calibrate our sensors offline in the shop and put them in calibrated. So diagnostics and in-shop calibrations really enable us to keep them fresh and on point. So altogether, our DO sensor, optochemical DO sensor, armed with the chip in the head with the ISM technology and armed with the anti-bubble OptoCap, is the hero for DO measurements. And then later on, they lay the foundation for the DCO2 measurement as well. So together with the DO and DCO2 gives you the complete picture around or completes the picture around the aerobic fermentation, because it gives you exactly a good picture how the supply of the nutrient, limiting nutrient oxygen is, and how the expression of the toxic byproduct, the DCO2, is. Thank you very much for your attention and for the time. And I thank the organizers again for this opportunity. I'll be more than happy to answer any questions, and the QR code is up there on the screen. You can scan that and ask the questions as well. Please do not be shy, unmute yourself, and I'll be more than happy to address your questions. Thank you very much.
Thank you, Dr. Ehsan. We encourage everyone to ask questions. This is your golden opportunity. We have 8 minutes of time, so enough time for you to ask any queries or make any comments as well. Please don't feel shy, as Dr. Ehsan said. Does anyone have any questions? We will also be sending a follow-up email with the contacts if you need to follow up with colleagues from Mettler-Toledo directly. And also you can view the video again and access the PDFs of the session after the event. Does anyone have any questions or would like to make any comments?
Absolutely. And Linda, I just posted my email address, and please, everybody, feel free to, if there are any questions or if there are inquiries about the cutting edge technologies, please let me know, and I'll be more than happy to help you out and shake your hand with the right contacts at Mettler-Toledo Process Analytics, or if your inquiries are about their control strategies, I'll be more than happy to address them myself or shake your hand with our academic partners. We have many esteemed academic partners that are helping us at all times, a continuous basis, with DO measurement and also DO maintenance strategies with inside the aerobic fermentation, both fermentation and cell culture. So we can be of assistance when it comes with your challenges with aerobic fermentation.
Thank you, Dr. Ehsan.
Of course, my pleasure.
We've still got a few more minutes if in case anyone has any queries.
I only see one inquiry for the PDF version of the presentation, and I think you addressed it. It's going to be posted, so they can download it once it comes through the email.
Yeah, that's right. We'll send the PDFs directly to everyone that attended, and they can access the details there. And then in a few days' time, we'll have this video posted up onto the ISPE Singapore affiliate YouTube page so that people can actually watch it directly off the YouTube.
Wonderful.
Okay, so I guess you have a very full day ahead of you, Dr. Ehsan.
Thank you very much. Yes, one of our large manufacturers here are awaiting us, and I'm sure one of the topics that definitely is going to come up is DO. So it was a good starter for me, refreshing my mind and remind me of some of the points. So I'll be putting them out shortly as well.
So we're very happy that you could use us as your warm-up session, as it were. Thank you for that.
Thank you very much. Thank you again for the opportunity. Real pleasure, and looking forward to be back perhaps next time with the dissolved CO2, as the momentum is still picking up inside the cell culture community. And I'll be more than happy to dive in and spread the word about how dissolved CO2 can be a critical process parameter as well.
Okay, well, thank you very much for that. But also thank you for today and for sharing your expertise with us. We look forward to another opportunity. We'd like to thank Dr. Ehsan, as well as all the people who've attended this morning's session. If you have any queries, as we mentioned, please do get in touch with us. We'll send you the contacts for follow-up. And until the next time, thank everyone for coming. Wish everyone a great day ahead. As it reaches the end of the week, also a good weekend. But again, thank you very much for all your support, and we look forward to seeing everyone again.
Thank you, Linda. Thank you, everybody. Bye.
Thank you all. Bye-bye. Have a great day.
Bye-bye. Have a good weekend.